Super! Hi everybody, I am super happy to be here. My name is, whoa, you see how everything's falling apart? It's live, right? It's Hacking with Swift live. It's exciting. So my name is John Sundell. Like Paul said, I'm the creator of Swift by Sundell, which is a weekly series of articles and a podcast about Swift development. But most importantly is that I'm just a Swift developer, just like you. And I'm really excited to be here today to give you a talk about a topic that is quite dear to my heart, which is about generics. So Paul asked me to do the opening keynote for this conference. And when he did, he asked me, well, John, would you like to do this? And I said, yeah, of course, that would be a lot of fun. And he said, well, the only thing I need you to do is come up with some lightweight, simple topic that we can use to kind of warm up the day. You know, nothing too complicated. Give people a little warm up. It's going to be great. And I said, don't worry, Paul. I got this covered. And what did I come up with? Generics. Right? So that's going to be a lot of fun. But you know what? These are gentle generics. So what I want to talk about today is how I think we can deploy generics in a way that is easier to understand and actually make our code simpler, not more complicated. And how I also think that generics is really key to fundamentally understanding how Swift works, and also with the new frameworks that Apple are introducing this year, like Swift UI and Combine, which makes heavy use of generics. But generics, they do have a little bit of a reputation in our community. When people hear this word, a lot of people think that, that they are complicated, they generate this really hard to read code, that it's really only relevant for people who build frameworks. It's not really something that we should use in app-level code. And some people might even go so far to say that using generics is kind of like over-engineering, that using concrete types is way simpler and just easier to understand. And I definitely agree that some uses of generics can definitely be described with these terms. There's a way to implement generics in a way that is really complicated, just like any other code. But I also believe that there is a lot of ways to use generics in a ways that actually make code simpler, not more complicated. And like I mentioned earlier, I also think that generics is really much more than just any language feature. They're a core fundamental part of Swift itself and a big reason why Swift can work the way it does. So if you open up your terminal and you type man Swift, which gives you the manual entry for the Swift compiler, you're going to get a description as the first sentence. And it reads like this, that Swift is a safe, fast, and expressive general-purpose programming language. Now you might notice there that the very first word in the sentence is safe. And as we all know, Swift puts a high focus on type safety and leveraging the compiler in order to produce more safe code that is less prone to runtime errors. And that's a big reason why many of us love Swift, because it lets us write code that is more robust. We no longer have to worry that we forgot to check that variable if it was nil or not, or that we are accidentally passing a string to an argument that accepts an integer, or something like that. And a big reason why this works in Swift is because of generics. If we look at a code sample here, we can see that we create an array of strings. It contains two elements, hello and world. And then we try to append the integer 17 to that array. Now, of course, this doesn't work. The compiler gives us an error. It says, you can't do this. You're trying to put an integer into an array that's supposed to only contain strings. And that's awesome, because that just removes a whole class of common programming errors. I think anyone who ever coded in Objective-C or in more dynamic languages like JavaScript have faced this issue where you accidentally mixed different objects in an array. So this is really great. And the only reason really that the compiler is able to give us this error message right here is because array in Swift is implemented as a generic struct. It's a generic over elements, where elements is array's generic type. What that means is that inside of the array type itself, elements can literally be anything. It can be any type, any class, an enum, struct, whatever you want, you can put it into an array. And that's incredibly powerful. And also makes it so that the implementation of array itself cannot make any assumptions about what kind of element that it contains. Now, that's really great also from a design perspective because it keeps the code within array focused on one thing only, being an array. And the way you can kind of look at this is that array is a generalization of a given concept. In this case, it's the concept of storing different elements sequentially in memory, which is what arrays do. But equally important is that this concept of being an array can then be specialized into any number of concrete use cases. So for example, we can create an array of strings. Now we've specialized that generic into being bound to the string type. And that's great because that enables us to make all those assumptions that the array actually contains strings. So the first thing we can really learn about generics overall is that they're all about generalizing a piece of code so that it's no longer bound to a single concrete type, and then allowing that generic code to then be specialized for any number of use cases, which is really cool. But of course, these days, generics is very, very, very topical and something that we really have to focus on as we're getting new frameworks from Apple that makes heavy use of generics and all those features that they contain. And of course, one of those exciting new frameworks is SwiftUI. I think everyone here in this room and everyone in the Swift and iOS developer community has this like mixed emotions about SwiftUI. That it's exciting, it's fun, we're eager to learn it, but it's also kind of scary. It's something that is really changing the way we're going to write apps. It's a big paradigm shift, and it can kind of be a little bit scary or stressful looking at all these really huge new changes. So let's take a look at a code sample from a view that we can build using SwiftUI. So here we're creating a contact list. It's a list that's going to display an array of contacts, and we're going to implement the body of this SwiftUI view. Now, one thing that I really love about SwiftUI, and I'm really, really excited about it, is just how lightweight the syntax is when you use it. It really removes a lot of the cruft that we previously needed to build UIs and just makes it so much simpler. So for example, if we want to build this list here, what we can do is we can start by creating a list struct and then passing in that array of contacts directly to the list. And that gives us a closure where we get access to each contact, and then we're going to create the view that's going to represent each one. So to do that, we're going to use the VStack type, which is a vertical stack. We're going to align all of our elements to the leading edge, which for left to right languages would mean on the left edge. And then we're going to create two pieces of text, one for the name of each contact and one for the email address of that contact. Now, this is really cool. Just imagine how much code you would have to write in UIKit to make this happen. You would have to start with a view controller, then a UI table view data source, and a table view itself, and cell configuration code, and on and on. And also, like I mentioned earlier, the syntax here is incredibly lightweight. There's not a lot of symbols, there's not a lot of extra words. We're really just focusing on what we're trying to achieve with this declarative UI description. But if we look a little bit beyond just the surface level of SwiftUI, and we start asking ourselves some questions. For example, what is the actual type of this view here? You can see here that we're using the sum keyword, which is a new feature in Swift 5.1, which is called opaque return types. It enables us to return any type that conforms to the view protocol as part of this computed property. So in this case, we're using list. So you might be thinking, well, since we're returning a list here, it should mean that the type of our view is list, right? We're just passing the contacts in to a list, so the type should just be list. Well, not really. In fact, if you inspect the actual result of this expression, this is the type that you get. For each, which is generic over array, which is generic over contact, and then it's got an H stack, generic over V stack, tuple view, text, text. Whew. Now that's what I call a type name. Well, we can look at another example. Here we have a little bit something that is a little bit more simple. We have a text. We are creating a text using one of our contact's names. And then we're just changing the accessibility identifier of that text to, for example, be able to UI test this. And then we're also changing the minimum scale factor of this label so that the system will be able to shrink it down to 0.5. Now again, what's the type of this expression? It should be even more straightforward, right? We're literally creating a text here and just modifying some properties. It should just be a text. Well, not really. Here is the type that we get. Modified content, generic over modified content, generic over text accessibility identifier, environment key writing modifier of CG float. All right. Well, you might be thinking now when you hear me say these things that I'm kind of making fun of SwiftUI or that I'm criticizing it, that this is ridiculous. Why do we have all these crazy types? And I know that Apple is working on simplifying these types and also improving some of the diagnostics and error messages that we can get from seeing these things. But I'm not criticizing SwiftUI here. Actually, I think the fact that this is true, that we have this simple API that just generates this type, is just a testament just how awesome SwiftUI is. Because if you think about it, we are not necessarily seeing all of these types when we're using it. All we see is this simple, nice declarative API. But then under the hood, all of these complex generics are created for us. Now, this is really powerful because it enables SwiftUI itself to retain type safety throughout the system. It can encode a lot of the things that we use when we modify our views into the type system itself, using things like accessibility identifiers and modifiers and other things. But at the same time, it doesn't leak those implementation details out to us. For us, we just get a simple, elegant top-level API. But at the same time, under the hood, generics is really what's powering everything. And I think this is really what generics should be all about. Generics should make our top-level code easier and simpler. It shouldn't make it harder. And if they don't do that, if they don't make it simpler, then generics is most likely the wrong tool for that problem. Let's take a look at an example that we might face when we're building some of our apps ourselves. So let's say that we are writing a drawing application, an application where the user is able to put different elements on a canvas. So we might have a function called draw. And this function here accepts a shape, so we pass a shape into it, and we're going to get an image back. And to do that, we create a drawing context, and then for each point in our shape, we add that to the context. And then finally, we return the result of making an image out of our context. So this is a really simple and nice function. It just has 3 lines of body. It's quite easy to understand. But then we start iterating on our app, and we want to add more features. Let's say we don't only want to add support for drawing shapes. We want to draw many more things. For example, we might want to draw an array of shapes. Like the user has selected a bunch of different shapes, and we want to draw them. And an initial idea on how to implement this might be to say, well, I already have this draw function that lets me draw a single shape. Let me now take that draw function and map over the array of shapes that I get passed in. I'm going to get an array of images back. And then I'm just going to write some kind of combine function that takes that array of images and just makes it so that it's just one image. Now, this is, again, a simple implementation. It's just 2 lines. But if we think about it for a little bit, it's not very efficient. Because what we're really doing here is that we're drawing each shape into its own drawing context, and we're even generating one image for each shape. And then we have to do the work to combine all those images into one. And that's really unnecessary computation we shouldn't have to do. And it might also slow down our UI. And if the user selects, let's say, 1,000 shapes and wants to draw all of those, our app might just start crashing or behave in really bad ways. So that's a bit of a problem. But equally important is that if we want to keep iterating on this draw function and add even support for more things as well, let's say that we want to be able to draw text, we want to be able to draw charts or icons or all sorts of other things you can imagine in a drawing application, we're starting to see a problem here where we're going to have to repeat our work over and over again and create different overloads and different versions of this draw function in order to make all of these different things happen. And if we think back a little bit to the beginning, where we looked at array, where array was a generalization of the concept of storing elements, where you could then specialize that concept to a given use case, for example, strings. Isn't the same really true here in our app, where we are also dealing with a generalized concept of drawing that we then want to specialize for shapes and icons and images and all sorts of things? That's really what we're dealing with here. But the problem in our current implementation is that the draw functions that we have created, they both act as the generalization of the drawing concept itself, and they also are the specialization for it. It's all mashed into one. And that's really what's causing our problem. We have a concept which should ideally be more generalized so that we can use it for many different things, but we have instead opted to make it concrete for each use case and duplicating a lot of code. So let's take a look at how we could fix this. The first thing we could do is we could take our drawing context type and turn it into a protocol instead. And the only requirements we will have for this protocol is that we can create a new drawing context just with an empty initializer, and that we can create an image out of a drawing context. Then what we can do is we can take all of our drawing code and make a protocol out of that called drawable. Drawable will be a generic protocol. And the reason it's generic is because it has this associated type. And the associated type here has a type constraint that says that in order to create a context, you need to conform to the drawing context protocol. Now this combination here is really powerful because it enables any drawable type, whether that's a shape, an image, a text, or anything else, to define what kind of context that it wants to be drawn in. And that's what makes it generic. But at the same time, we've added a constraint on that generic to say it needs to conform to drawing context. And that way, when we are writing code against it, we know that we will always have an empty initializer, and we will always be able to make an image out of each drawing context. Now, that's really cool because it enables us to take all those drawing functions that we had before, all those different overloads and all that complexity, and really reduce it to just a single function. We're going to call it image from, just to make the naming really clear. You're taking any drawable here, and again we have a generic constraint here to say that this function can be used with a type that we call D, and D can be any type that you want. That's again the power of generics. It's a generalized concept, but you need to conform to drawable. So pass in any drawable that you want here. Now, just like how we talked about earlier, how array couldn't make any assumptions about what kind of elements it stores, the same is true for our function here as well. We cannot assume that we're drawing a shape or we're drawing a text or any other concrete type. We just know that we're drawing any drawable. But that's great, because that way we can create this implementation which is extremely generic, where we can create a context using the associated type from the drawable protocol, and then we can just tell the drawable to draw itself in that context. And finally, because we have that make image requirement, we can call our context and make an image out of that. And we can reuse this function for any drawable that we can think of, either now, all the types we already have, or in the future, which is pretty cool. So what we can do is we can go back now to our existing code, for example our shape, and make it conform to drawable. Implement the draw in context function, and it can decide what kind of context it wants to be drawn in. For example, since it's a shape, it might be drawn using vector graphics. So here we put that same code we had before of iterating through the points and adding them to the context. But we can also do the same for any other type that we have. So for example, we can extend our text type to say that this is drawable, but in a text drawing context, which supports things like fonts and strings and text-specific properties. But both of these types can then be used with the same function that generates an image from them, which is really, really powerful. So what we've done here really is we've generalized the concept of drawing into a drawable protocol. And then we've created specializations of that, such as shape, text, and image, which can each define their own context that they're drawing in. Now this gives us the power of having a generalized concept which doesn't make any assumptions about what kind of drawing it's doing, but at the same time it gives us the flexibility to implement as many as many drawables as we want, because it's a protocol and it's completely generic. So another way of looking at what we've essentially done here is that we've taken a bunch of different use cases, like drawing images, texts, shapes, etc., and we've built a common shared API on top of that. Now, having a shared API is not only great for code elegance kind of sake, it's also great for learning or getting into a new code base. If you think about it, before, we had all these different drawing functions where if someone new joined our team, we would have to go through each and every one of them and explain what each drawing function does. Now we can just point them to this image from function, and that's all they need to know in order to use our drawing code, which is really cool. But also equally important is that we don't only have this shared API, but once we have that, we can actually build really powerful abstractions on top of that shared API because we have that common foundation. So a few different things that we can do to make our code even easier to work with and build convenience APIs is that we could do something like we can extend array, which again is a generic. So we can say that array will now conform to drawable when the elements in that array also conform to drawable. And then we can implement draw for an array, but not for any array, just for the ones that contains drawable elements. And then we can retain the type safety, just how Swift UI used generics to retain the type safety. We can do the same thing here, where we are making sure that we're drawing in the same context type for each of our elements as the elements themselves are. And here now you can see that we've actually, through this, fixed the problem that we originally had, where we were previously drawing an array of shapes using an n number of drawing contexts. But here, we can pass the same context and draw all of the elements in the array into the same context and just generate one image, which also will help performance. But the cool thing is that even though this code here might look a little bit more complex, it's an implementation detail. As the API user, as someone using our code, they don't need to know about these details. They can just create an array of shapes and then just say image from on it and get an image back. It's super, super simple on the top level. And that's really where generics really shine. Another thing that we could do is that we could create more generic types that helps us do drawing in more powerful ways. For example, we could implement a layer type that applies some kind of transform to an array of elements, and that again conforms to drawable. The cool thing about that is that we can introduce all these new types, and we can still use that same image from function with any of them, because we don't need to keep implementing the same thing. So what we can see here through this example is that generics are really great when we want to reuse some of our core logic for different use cases. And they can let us build these powerful shared abstractions that can be applied to any of those use cases. The same way as when you extend array or dictionary, you can have that applied to any code that uses them. The same thing is true here since we've built that shared layer using generics. Now, when you hear this talk here, and you've seen some of these examples, it might remind you of a principle or a way of working that has become really, really popular in the Swift developer community. And popular is a good way of describing it, because what I'm talking about is, of course, POP. And POP is what many people refer to as protocol-oriented programming. Now, protocol-oriented programming and generics are very, very highly related. You usually use protocols to define some kind of shared API that you're then using with generics. And I think protocol-oriented programming is great. But I think sometimes when you hear this word or this phrase, protocol-oriented programming, when you hear people talk about it, when you hear talks such as this one, which talks about how great generics are and how they can let us reduce our code and make it so much simpler, it's easy sometimes to get the impression that this should be something that we should apply everywhere. And I've worked with many teams where that has been the case, where protocol-oriented programming has become so popular that people have started to create protocols literally everywhere. For every single type, there's a protocol. For every API, there's a protocol. Even if we might not need it right now, we just create a protocol because it's protocol-oriented programming, right? Well, you know this common expression, which is that if all you have is a hammer, everything looks like a nail. Well, I think the Swift developer equivalent of that is if all you have is generics, then everything looks like it should be a protocol. That's an ancient Swift proverb, very, very old, found in the ancient scriptures. So just to look at an example of where I think these things can go wrong, where generics might not be the right tool for the problem, or where protocols might not be the right abstraction, is something like you look at one of your models, like you have a contact model, like we were using before when we were drawing our contact list. It's a very simple type. It says a name and an email. But you might be tempted to say, well, you know what? I think I can generalize the concept of being a contact. So I'm going to create a contactable protocol, because of course all protocols need to end with able, right? And then we have a name and email here. It's defined in this beautiful protocol-oriented way. And this is going to be awesome, because now I can have this perfect vision of the future. I'll have this beautiful system I built. I will dream about it. I will have like a listable protocol. It's going to have a contactable element. And then I'm going to have a list manager. And it's going to be able to take any array of contacts, which are contactable. And I can just render them. It's going to be so, so great. Well, these things can be fun to do as a hobby project, or to learn different language features, or just to impress your coworkers around how many Swift features you know how to use. But it's not really great from a perspective of making our code simpler. So if you look at it, what's the reason that generics is not really the right tool for the job here? Well, again, I want to use that simple flowchart I've been showing you a few times now, which is like generics are great when we want to generalize a problem and then create multiple specializations of it. So in this case, we have our contactable generalization, but it's just about being a contact. In our specialization, we only have one, and that's also being a contact. So it doesn't really make any sense. The generalization and the specialization are exactly the same. And I think this is a good thing to keep in mind when deciding whether or not to deploy protocols or generics or any of these more advanced features, is that generics, they are a great tool. They really are. But they're not a goal. The goal of our code should not be, let's use as many generics as possible. That would be a pretty crazy goal. So instead, making code generic should be in reaction to an actual demand, something that we've seen as a problem in our code base that we want to refactor to support. Not because we think we might reuse our logic sometime in an ideal version of the future. Because if we spend all of our time optimizing for the future, chances are high that that future will actually never arrive, and we've just done all that optimization work, well, pretty much for nothing. So when we think about protocol-oriented programming going forward, I think it's important to stick to the fact that it should be oriented around protocols, but not obsessed with protocols. That's, I think, what's really important to keep in mind. So to sum up this morning talk about a very lightweight topic, I think that generics, they're truly great when we want to model a concept, a given concept that's a generic one, for multiple use cases. So think of array, think of this drawing function we have, think of any use case in your app where you have multiple use cases for the same functionality, which could be generalized into a more generic concept. That's what generics are really good for. The goal of deploying generics should be to make our top-level code simpler, not harder or more complicated. Again, it's not about showing off how many Swift features you know how to use. It's about making our code better. And generics can be a great way to achieve that, but it's not a silver bullet. It's not something that should be used for every single use case, especially if we don't have those multiple different use cases. And then finally, when used in the right situations, generics can be incredibly powerful. And they can let us reuse both code and concepts throughout shared abstractions. So just like how we created an image from function that could be used with any drawable, that didn't only enable us to share code, it also enabled people on our team to share knowledge easier, because they only needed to learn that one function instead of having to learn all these different variations of it. And I think if we keep these three things in mind, what we can do is we can make generics a little bit easier to use and a little bit more gentle. Thank you very much.